This is Porterville College Physics 104A Homework Solutions. Chapter 4, starting with number 13, the railroad locomotive. First we need to convert these units to MKS units. So the mass of the locomotive, you should have 61 times 10 to the 6 grams. 10 to the 6 is mega. And that's going to be 61 times 10 to the 3rd kilograms. The force is 0.12 times 10 to the 6 newtons. So the acceleration, A equals F over m, and you get 2 meters per second squared. Part B, we have a greater mass, so it's pulling both of those masses added together. When you add them together, you get 1.461 times 10 to the 6th kilograms. And so the acceleration is force divided by mass, and so it's reduced to 0.082 meters per second squared. Number 18, starting from rest. Race car. You're given its mass, its displacement, initial velocity 0, time 4.95 seconds. So we need to find the average force, and first thing we need is the acceleration. So this is where kinematics comes in. If you use this equation, x equals x naught plus v naught t plus 1/2 at squared, x naught and v naught t go to 0, and we're left with x equals 1/2 at squared. Solving for that, acceleration is 2x over t squared. We get an acceleration of 32.6 meters per second squared. Now we can plug that into F equals ma. I use these averages because we don't know physically that it had constant acceleration, but we can use average force equals mass times average acceleration, and we get 30,700 newtons. Number 23 can just barely lift 35 kilograms on Earth. How massive a block could she lift on the moon? Here's one way to set this up. The force with which you can lift something is that thing's weight. Let me say that again. Let me say that another way. If you can just barely lift something, whatever its weight is, that's the force with which you can push. So the force with which she can push is the weight of the object on Earth. It's also going to be the weight of an object on the moon, or the weight of an object anywhere. So the weight of an object on Earth is going to be its mass, and I call that me, times g on Earth. And that's also going to be equal to m moon times whatever g on the moon is. So we're solving for what is the mass of an object that she can lift on the moon. So m sub moon equals, and I've just set these two equal to each other, and I've solved for m sub moon. So m sub moon equals m sub Earth times the ratio of the two strengths of gravity, Earth divided by that of the moon. So now we plug in the numbers. The mass of an object she can lift on Earth is 35 kilograms, times g on Earth is 9.8 meters per second squared. G on the moon, you can get this from the appendix in the back of the book, 1.62 meters per second squared. This ratio comes to be about a 6-to-1 ratio, which means you can lift something 6 times more massive on the moon than you could on Earth. So that ratio, which is roughly 6 times 35 kilograms, she could lift a 212 kilogram object on the moon. Number 27. A 50-kilogram parachutist descends at a steady speed. What force does air exert on the parachute? Let's draw a force diagram. The weight pulling down, drag from air pushing up. We start with F equals ma. The sum of the forces equals mass times acceleration. And since it's at a steady speed, acceleration is 0. So the sum of the forces, I've got here force of the air I make that positive because it's up, minus the weight, I make that negative because it's down, equals 0. Which means if something is dropping at a steady speed, that means that the force of the air is equal to the weight. Notice that it's irrelevant how fast it's dropping. What's most important here is that it's dropping at a steady speed, so acceleration is 0. So the force of the air is the weight, 50 kilograms times 9.8 newtons per kilogram, 490 newtons. Number 29. An elevator accelerates downward. What force does the floor exert on the passenger? So we're doing a force diagram. This dot here represents the passenger. We have the weight of the passenger going down. The force that the floor exerts on the passenger, that's the normal force. So once we draw the free body diagram, and we'll acknowledge that up is the positive direction, down is the negative direction, we do F equals ma. The sum of the forces, positive n plus negative mg, so n minus mg equals ma. And then we solve for n, because that's the force that the floor is exerting on the passenger. So we get that n equals mass times g plus a, with a little algebra. Plug in the numbers, Mass is 52 kilograms, g is 9.8. Acceleration, since it's accelerating downward, that's the negative direction, we have to make that negative 2.4. So we get normal force is 385 newtons. Number 33, what upward gravitational force does a 5,000 kilogram elephant exert on Earth? This has to do with Newton's third law. Recognize that by Newton's third law, whatever force the elephant is pulling up on the Earth, that's the same force that the Earth pulls down on the elephant, and that is the weight of the elephant. So we can say that the force that the Earth is being pulled up on, I've written here force on the Earth, is equal to the weight of the elephant. 5,600 kilograms times 9.8 newtons per kilogram, and we get 55,000 newtons, or 55 kilonewtons. Number 35, what force is necessary to stretch a spring 48 centimeters if its spring constant is 270 newtons per meter? Okay, this basic Hooke's law here. Sometimes we use a negative sign with Hooke's law. That just indicates direction. We're more interested in the absolute value of the force. So I'm just saying absolute value of the force equals k times x. K is 270 newtons per meter. X is 0.48 meters, and we get 130 newtons. Number 37. A spring with constant K is used to weigh a 6.7 kilogram fish. How far does the spring stretch? Let's set up a force diagram. The object is the fish that's hanging, so the spring force is pulling it up. The weight of the fish is pulling it down. If it's balancing there in equilibrium, what we're going to find is that those are equal to each other. But let's use F equals ma to find that out. Sum of the forces equals ma, force of the spring going up, minus mg going down. It's not accelerating, so equals 0. And so what you see is force of the spring is equal to the weight of the fish. Now, I've right here in this next step turned force of spring into kx. Kx minus mg equals 0. So we solve for x equals mg over k, plug in the values, and we get 0.19 meters or 19 centimeters. Number 45. There are two ways to go about number 45, a complicated way and a simple way. And it's not just simply a matter of picking the simple way over the complicated way. Physics problems, you don't know ahead of time which way is going to be the simple way or the complicated way. It just depends on where your thinking goes as you're evaluating the problem. I'm going to show you two different ways. So the more complicated way I'm going to show on this yellow sheet, and I've switched colors, so if you are not interested in watching this more complicated solution, you can just fast forward on YouTube and just keep fast forwarding till you get back to the white sheet of paper, and we'll pick it up on the easier way. But I do recommend you take a look at this. So we have these three blocks in a line, and we're pushing just on the first block with 12 newtons of force. And the first block pushes the second pushes the third, and they're all accelerating at some rate. We have to find what that acceleration is. And then ultimately, what force does the middle block exert on the rightmost one? That's the question. What we're going to do is, and again, this is the more complicated way, and then when we switch back to the white paper, I'll show you a very easy way of evaluating this. We do force diagrams for the three separate blocks. Block 1 has force of the push, that's F sub P, pushing to the right, force of 2 pushing on 1, that's like a normal force between 1 and 2. So 2 pushes back on 1. For block 2, block 1 pushes on 2 to the right, block 3 pushes back on 2. For block 3, block 2 is pushing on block 3 to the right. Nothing is pushing back to the left. Now, we apply F equals ma to all three of these separately. So for the first block, we have force of the push. I make positive the right direction, negative the left direction. Force of the push minus force of 2 on 1 equals, and excuse me, I wrote the letters in reverse order of how I usually write it, acceleration times mass of 1. Which leads us to, then I just plug in the values. 12 is the force of the push, minus force 2 on 1. I plugged in what the mass is. The mass of 1 is 1 kilogram, so that just leaves A. And we'll leave that there for right now. Block 2, let's evaluate sum of the forces equals ma. Force of 2 on 1 minus force of 3 on 2, which is to the left, equals acceleration times the mass of 2. In the next line, I've plugged in the mass of m2, which is 2 kilograms. Let's leave that right there for the moment. Block 3. There's only one force pushing on it. Force of 2 on 3 is equal to acceleration times mass of 3. Mass of 3 is 3 kilograms, so I've plugged that in there. Now, one thing I want you to notice, I've done some subscript shifting around because for block 2, I wrote here force of 1 on 2, and then you'll notice in the math, I wrote force of 2 on 1. I shifted 1, 2 to 2, 1. Well, the reason is, by Newton's third law, the force that 1 pushes on 2 is the same as the force that 2 pushes on 1. So I can make them equivalent, and that reduces our number of variables. Same here, force of 2 on 3, you notice force of 2 on 3, but in this line I called it force of 3 on 2. And I just did that to reduce the number of variables because I recognize by Newton's third law that those are the same. So now I've got this equation, and this equation. 3 equations, 3 unknowns. We should be able to use algebra to solve this. Here's the method I use. You can use whatever algebra you want. You can use a system of linear equations. I just chose to do it this way. I took this value that force of 3 on 2 is equal to 3a, and I plugged it into this equation. So force of 2 on 1 minus, and here I call it 3a equals 2a. And I solve that and I get force of 2 on 1 equals 5a. Now I take that and I plug it into this equation. 12 minus force of 2 on 1, which I now call 5a, equals a. 12 equals 6a, and I get acceleration equals 2 meters per second squared. Now again, that's just the algebraic method that I use to solve this. You can use whatever method you're most comfortable with. But in the end, we get acceleration equals 2 meters per second squared. This doesn't answer the question that the book is asking, but this is a necessary step we need to find acceleration. Now, I'm going to show you a simple way. So switching to the white paper, a simple way to evaluate what is that acceleration. Okay, it's going to be so much easier. Here I have, first of all, let's just consider not the separate blocks, but, well, actually, hold on. This is just setting up the question. We want to know the force of 2 on 3, because that's what the question is asking, equals mass of 3 times acceleration. So this is the free body diagram, or the force diagram, just on block 3. And we know the force, well, we don't know the force. We're trying to figure that out. We know the mass of block 3, it's 3 kilograms, but we don't know the acceleration. So the question is, what is the acceleration? Well, I just went through the yellow page showing detailed the breakdown, how we can figure out. But here's an easier way. Consider the entire system of blocks, not the individual blocks, but all 3 of them. They're all moving together as one unit that has a mass of 6 kilograms. So considering them all as one unit, force of push equals the mass of that unit times acceleration, which means acceleration is force of the push divided by the mass of the unit. 12 newtons is the push, 6 kilograms, and we get an acceleration of 2 meters per second squared. And that's a whole lot easier than what I did on the yellow page. Now, we come back up here and we see force of 2 on 3 equals mass of 3 times acceleration. So we plug that in. The mass of 3 is 3 kilograms. Now we know that the acceleration is 2 meters per second squared. And so we get a push of 2 pushing on 3 of 6 newtons. Number 52. Frog's tongue. Okay, this is basic F equals ma, but we have to be careful with our units. If we're going to get in newtons, we need MKS units. So the mass is 500 milligrams. So here I've shown the conversion from milligrams to kilograms. 1 milligram under 10 to the negative 3 grams, because milli means 10 to the negative 3. Then we need to convert from grams to kilograms, so 10 to the third grams under 1 kilogram. So milligrams, milligrams divide out, grams and grams divide out. We're left with kilograms. 250 meters per second squared. We multiply all that by. So the mass, when we've done the unit conversion, is 5 times 10 to the negative 4 kilograms. Times the acceleration, 250 meters per second squared, so you should get 0.125 newtons. Make sure that you understand and then that you can competently do metric conversions like this. Number 55. Okay, what engine thrust is needed to accelerate a rocket as downward, upward, and so forth? Okay, I draw a force diagram. Now, there will be times in these different problems when the force might be directed up. Sometimes it will be directed down. Let's just have one general force diagram where we don't have to worry so much which way it's going up or down. Just let the math tell us. So let's make the force go up, as you see in the diagram. And what's going to happen is, if we solve for a force being positive, we know that that is the true direction, it's up. If we mathematically solve the force to be negative, that will mean it's in the opposite direction of what we've drawn, and it's down. So we'll just arbitrarily start by saying, drawing that force going up. So question A, we can start with the sum of the forces equals mass times acceleration, which means force is up. So it's positive minus mg, which is down, equals ma. We solve for force, it's m times g plus a, and now we plug in those values. M times g is, we can just call that 1g. Acceleration is downward, 1.4 g, so that's going to be minus 1.4 g. It's really plus negative 1.4 g. And what we get is negative 0.4 mg, or we can say, since it's negative, we can say 0.4 mg downward, and that's the force. So in this case, given that's negative, we can see that truly this diagram should have had the force pointing downward, but the negative shows us that. For question B, we've already done the derivation in question A up to this point, f equals m times g plus a, so I don't reproduce that, I just rewrite it here. And then we plug in for g, that's still 1g, but now it's an upward acceleration of 1.4 g, so I have plus 1.4 g, and we get a force of 2.4 times mg, or 2.4 times the weight of the rocket. And since it's positive, we can say that's upward. Question C, we could use the same formula that we did in A and B. We could use this formula right here and just call G 0, and that would lead us to F equals ma. Or we could redraw the diagram, and since there is no gravity, the only force is the upward force. And then when we apply F equals ma, since that's the only force, we just get F equals ma. So force equals mass times, and then the acceleration is 1.4 g, and so we get 1.4 times the weight of the rocket. Number 60. Railroad car is being pulled beneath a grain elevator. Now it says use the result of problem 59. So we have F equals ma plus v times dm dt. And by the way, it would be a neat exercise. It's a very quick thing to do, to go back to 59 and solve for this. It takes about only 1 or 2 lines. But here it is given to us. So now we plug in the values. It's moving at a steady speed, so there is no acceleration, 0. But then we have this additional value, plus v dm dt. V is 2 meters per second. The rate of mass change is 450 kilograms per second. So we get 900 newtons. Number 67. Find an expression for the maximum jerk. I'm trying to figure out a punchline for that. Haven't figured one out yet. Find an expression. Okay. F equals ma, and it says that the force is F naught sine omega t ma, so there's acceleration. It defines jerk as the rate of change of acceleration. So this mostly is all one calculus problem. So dA dt, which is J, I've used the abbreviation J for jerk, dA dt, your calculus should show that you get F naught over m times the derivative of sine omega t, and that should give you F naught omega over m cosine omega t. That's the expression for the jerk. Now we need to find the maximum of it. We use calculus to find maximum and minimum, to find all those turning points. Then we'll have to evaluate which is the max and which is the min. But the way we do it is we take the time derivative of jerk, so dj over dt, and we set it equal to 0. So when you take the time derivative of j, you should get negative F naught omega squared over m sine omega t, and set that equal to 0. When you solve for where is that equal to 0, recognizing that F naught and omega squared and m are all constants, we're looking at where is this sine function equal to 0? Well, that's going to be where the argument of the sine, or omega t, is equal to 0, and you think about going around the unit circle, 0, pi, 2 pi, 3 pi, 4 pi. Every multiple of pi is where sine is going to equal 0. So the solution for the turning points of jerk is 0, pi, 2 pi, all the way up to n pi, all integer values of pi. Now, we need to figure out which is the maximum, which is the minimum. Now, one way you could do this, and I haven't done it here, is to find the second derivative. And the second derivative tells you maximum and minimum. If the second derivative is negative, it's a maximum. If it's positive, it's a minimum. I have a different way of doing it. I just try different solutions. So let omega t be 0. Plug it into the formula for j. And you get j is positive f naught omega over m. Now, plug in omega t equals pi. Plug that in here. And you get that j is negative f naught omega over m. And before long, you find that it alternates between 0 is the maximum, pi is the minimum. Then it's going to be 2 pi is the maximum. Omega t equals 2 pi gives a maximum. Omega t equals 3 pi is a minimum, and it alternates between those. So now we'll figure out, okay, what is the expression for the maximum? Let's just take 0, plug it into j, and we get f naught omega over m times the cosine of 0, which is just f naught omega over m. And that concludes the Chapter 4 homework.